just waiting on some people. Waiting for everyone to get in. Dang, we have a lot of people. Okay, go ahead. Okay, so do you guys want me to finish working out problem 9? Or does everyone feel all right with it already?
Yes, please.
Can you continue it, please?
Sure, no worries. All right, so where were we at? We is it not? Okay, it's not working. We drew down what was losing heat and what was gaining heat, right? So negative Q and H2O, right? And then, okay, so how do I set this up? How do I begin it? First of all, do I have all my variables needed to calculate my final temperature?
Yes.
Okay. So H2O and delta T. Okay. So you guys said I have all my variables, so I'll go ahead and start plugging in. So my mass here, it's 1388.2 grams. Our specific heat of iron is 0.444 joules per gram degree Celsius. And then our change in temperature, our final temperature minus, what is our initial?
0.
0.
Yeah, 0 degrees. And then how do I set up the water portion?
1297 grams. And then 4.128.
184, I think I wrote that number wrong, remember?
Sorry. Oh, yeah, that's true.
Joules per gram degree Celsius, and then what else?
TF minus 96.77
degrees Celsius. Okay, sorry, it's pretty scrunched up. And then, okay, so after this, what do you guys think I should do? So after this, what did we do?
After this, you should multiply 1388.2 times the specific heat, which is 444.
And then what number do you guys get when you multiply that one out?
Wait, sorry. So do you have to solve for the final temperature? No.
I'm sorry?
Do you have to solve for the final temperature?
Yes. Here we're solving for a final temperature.
Okay.
There, the number I got was 616.36.
Okay. 616.36. What's our unit, just so we know?
Joules.
Joules. And we're missing our Celsius. We haven't canceled that one out. And we have a TF minus 0 degrees Celsius. And then what do you guys get when you multiply the water portion? Better have my chat.
I got 5,426.65.
5,426.65.
Yes.
And then this is also joules per degree Celsius. And then we have our final temperature. That's really messy, minus 96.77. Okay, so there we go. So after this, what should I do?
Basically multiply those, basically multiply by TF and negative 0.
So I distribute, and then I do the same over here. So over here, I have 616.36 TF equals to negative 5426.65 TF. And then I don't know what this other big number is.
It's a large number.
525,137.
Yeah, it's a pretty big number. Thank you. Okay, and then after this, what do I do?
You move the negative 426.65 final temperature to the left.
Yes. 426.65. Okay, and then once I do that, what number do you guys get?
6,043.
6043. TF equals to 525.137. And then,
Yeah, you divide 5 to 5 by
yes.
that. Yeah.
And then what's my final temperature?
86.9.
86.9 degrees Celsius. There you go. So is that correct in your answer document?
Yes, sir.
Yes.
Any questions? Everyone pretty good?
Yeah, all good.
Okay. So, all right, you guys said you guys wanted to do the first question. So let's do the first question because we did skip that one. Okay.
When do we use, so for this last one, we use Celsius, right? For which equations do we need to convert to Kelvin?
Kelvin, you have to do that for ideal gas equations.
Okay.
In this case, the reason why we don't have to convert to Kelvin is because our specific heat is already in degrees Celsius.
Okay, thank you.
No problem. Okay. All right, so our first problem. So here we're asked to ask the enthalpy of formation of C3H8 in the gas formation. So this problem is pretty difficult if you guys don't understand what enthalpy of formation means. What does the enthalpy of formation mean? Anyone have a idea or definition?
Well, is it like the change in well, I guess I'm kind of repeating the word in itself, but it's the change in enthalpy when 1 mole of a substance is in the standard state.
When it's formed in its standard state. You're correct about that. So what forms C3H8? If I want to make it, what elements would I need?
C and H.
Yeah, I need carbon and then hydrogen. And then how do I balance this out? If I want this to remain 1 mole.
3
Mm-hmm.
and 3.
And then 8. Yeah, and there you go. This is your reaction to, this is the enthalpy of formation that we need. So this is our target equation. So although you guys weren't given your target equation, it's implied that you guys sort of already know how to do it. Is there any questions on how I got that equation?
Yes.
What's your question about it?
How did you make it up?
So enthalpy formation, this is what it means is the formation, or you basically make 1 mole of compound from its elemental elements. So in this case being carbon and hydrogen, since those are the elementals. What's wrong with hydrogen actually? I'm so wrong here.
Yeah, it was oh wait, it was 4, no? No, wait. Oh, sorry.
What type of atom is hydrogen when it's alone?
It's diatomic, so it should be
Diatomic.
H2.
There you go.
And the coefficient.
Oh, you cut yourself up.
4.
There you go, 4. Thank you. Yeah. So basically here we're making 1 mole of compound from elemental substances. That is what enthalpy of formation means. So that's how you derive the equation. So here we have, this is our target equation. So what type of method am I using here, first of all?
Direct.
Indirect.
Indirect. How do I know if it's indirect?
You're giving a lot of chemical equations.
Yes, you're given a ton of equations right here. And then, so our first equation, what do I have to do? How do I fix it?
You have to reverse it.
Yes, I have to reverse it. So 3CO2 plus 4H2O. And then this yields 5O2 and plus C3H8. Thank you. Is there anything that I have to do in order to
Thank you for calling Metro by T-Mobile, America's 5G network leader. How can I help you
I'm gonna
today?
go ahead and mute you just in case.
You would switch the negative 2,219 to positive.
Yeah, so I have to switch that. Okay, is that all I have to do for this equation?
Wait, I have a question.
Yes.
Why did you switch it up to positive?
So the reason why is because if we flip our equation and we flip it to the other side, our enthalpy also changes. So instead of releasing energy, it now absorbs energy.
Oh, okay. Thank you.
That's anytime we switch our equations. All right, so am I done with this equation? Do I have to do anything else?
No, it's done.
No.
Yeah, it's done. So our second equation, what do I have to do?
You,
Multiply it times
multiply-
3.
Yeah, multiply and sign 3. So I have 3, and then this is graphite, and then plus O2, 3O2.
It's 4 now? Oh, no, wait, sorry.
Yeah, so we're looking at carbon here, so it would be 3. And
Yeah,
then
yeah.
3 CO2 gas. And then what do I do to my enthalpy?
Well,
You also
um,
multiply times 3.
I multiply it by 3. And then our last one, what do I have to do?
Multiply it times 4.
So my last one I have to multiply by 4. So 4H2O plus 2O2. This yields 4H2O liquid. Okay. And then I multiply this one by 4. How do I check if I end up with the correct equation?
You look to see which ones can be eliminated. Make sure you get back to the original equation.
Yes, exactly. So there's two methods. One of them, you can just straight up cancel them out. The other one is you write all the reactants, all the products, and then you start to eliminate on both sides. Okay. I'll explain how you get your target equation right now. So how do we, which compounds do we cancel out?
CO2.
3 CO2s
My 3 CO2s.
or H2O.
Those and 5 oxygens.
Yes, my oxygens. These two here, these will make 5O2. So these cancel out with the oxygens up there. And then what am I left over with?
3 Cs and
C
4
plus
hydrogens.
4H2.
You C3H8
H8. Yeah.
gas. Okay. So I ended up with my target equation. That means all of this is correct. So that means I can do my summation. So go ahead and calculate that. And what number do you guys end up getting?
Well,
I got negative 103.8 kilojoules per mole.
Okay. You said negative 103.
103.8
Mhm.
Okay.
kilojoules per mole.
Kilojoules per mole. And is that correct based on
Yes.
Okay. Yep. There you go. So your answer is D. Okay. So to explain enthalpy of formation, let me check your workbook real quick. There should be a definition in there. So in your workbook in page 206, in the paragraph under direct method, in that very large paragraph right there, near the end, it states what enthalpy of formation is. So basically enthalpy of formation is we make 1 mole of our compound from our elemental substances, or in this case, from its elementals and its elemental states. So in this case, the only compounds that make C3H8 is hydrogen and carbon. And all we have to do is balance the equation to make sure that we have 1 mole of the substance.
Diego, on the test, are they most likely gonna make us make our own target equation, or are they gonna give it to us?
I can't guarantee that. Yeah, I don't know how Dr. Saupe is doing the test. If he's giving you guys these types of problems as examples, it's possible he may, but I can't guarantee it.
So if they
Okay.
don't, just do like what you just did.
If it says enthalpy of formation, I would say it's safe to say yeah.
Okay.
And I don't think he would give you like a very complicated compound to make the target equation from. If anything, it'll be very similar to this. So it's only two elements, right? Carbon and hydrogen. I think the biggest thing is that you need to know that hydrogen is diatomic and carbon is not, right? So those are the only two elements we're going to use to form that new product.
Okay. Thank you.
Mhm.
Paulina, do you want to cover the next couple of problems?
Yeah.
Okay.
So
What was the acronym? No, the mnemonic for the diatomic elements?
Yeah.
Have no fear of ice cold beer.
Yeah.
Oh, they were muted.
Sorry, yeah. H2, N2, F2, OF, O2, sorry, I2, Cl, and Br2.
Yeah, so don't get confused with C. It's not carbon, it's chlorine. You can remember like cold Cl. Just be careful with that. And also with beer, boron, it's not boron, it's bromide, right?
Yeah.
Bromine. Okay.
Do you want to annotate on this one, or do you want to share your screen?
I think I can go ahead and annotate on this one if you just zoom in a little bit, please.
Sure.
There we go. Okay. Reduce number. Okay. So number 16. Right. So for carbon dioxide gas, the enthalpy of formation is negative 393.5 kilojoules per mole, and for water, it is negative 285.8 kilojoules per mole. Find the enthalpy of formation for C6H6. Right. So we want to find the formation of this, but on our target equation, or on the equation that they give us, it's on the left side, right? So we know we're going to need to switch that around. So if we switch it around, what are we going to do?
You have to change the sign
Yep, we
from
have to,
negative to positive.
exactly. So this is going to become positive 6.535 kilojoules. All right. So now we're going to have 12 CO2 gas plus 6 H2O. And that's going to yield 2 gas and 2 C6H6 liquid.
Is a direct method question?
Yes. Because they're only giving you one equation. Okay, so remember, like Diego mentioned earlier, we want to have 1 mole of the compound that we're making, right? So what are we going to do with each of these coefficients?
You multiply them times the value of what they have in there, what they give you. So for example, if you have 2C6H6, you would multiply times negative 93.5.
I think what you're asking, Paulina, is we want just C6H6, so we divide a whole equation by 2.
Yeah, so we were getting a little bit ahead. So right now, we just want to get the coefficient of C6H6 to be 1. So if we divide that by 2, we have to divide all of them by 2, right? And what else do we have to divide besides the coefficients?
Negative 6,535.
Yeah, our enthalpy of formation for the reaction, right? So now we're going to have divide everything by 2. So we'll get 6 carbon dioxide now, 3 water, I'm going to go ahead and leave this as a fraction. And then our 1 mole, which is what we were aiming for. Okay. And then we need to divide this as well. So you can tell me what they get when they divide this by 2.
I have a question.
Yes.
Why did you change the sign again? The 6,000?
Of the reaction? Because we switched the equation around. So because we made the products the reactants, whenever you have a reaction, it's going to take a certain amount of energy to make those products, right? If you flip it around and make the opposite products, it's going to take the reverse amount of energy. Does that make sense?
And how do you know
Will you always change it?
Mm-hmm. If you switch the products to reactants, you will always change the sign.
Oh, okay.
How do you know you had to switch it up? Is it because you need to find the thing for C6H6?
Yes, exactly. We wanted to have C6H6 as a product because we're finding the enthalpy of formation, right? So if we're finding the formation, we know we're making it as a product.
Can we just put it into the equation, like just how it is? The one that's like delta H reaction equals products minus reactants?
I don't think it would give you the correct answer just because, let me see. So we can try it. Right?
Demonstrated how?
That's the way I did it, and I think it does work.
It does work? Okay.
Yeah, I think if I remember correctly.
Okay, then you could, it does. Okay, cool. So yeah, so if you're doing direct method, then you could do it that way. I just kind of like to think it through because for other questions, it's going to be beneficial, like to know, like, I guess like the right way. Like, I think this is kind of like the easier way if you just leave the coefficients like that. But you always know that the enthalpy of formation is 1 mole of your target product. So that's just like an important concept to understand. But I guess in this case, it does work out the same way. So let's try it the way I'm doing it, and then you'll know that both will work. So whichever way is easier for you, just go ahead and do it that way, but let's try it. So what is our next step after this? So we divided this by 2, so what did we get here?
3,267.5.
Perfect, okay. So now we know that, I'm gonna run out of room here. Okay, so we know that the enthalpy of formation for the reaction is going to be equal to what? What is the equation that we use?
The
products less the reactants.
Mm-hmm. So is it products plus reactants?
Products less minus reactants.
Yes, minus reactants. So I'm going to put P. We know that that's products minus the summation of the moles and the enthalpy of the reactants. Okay. So if we plug that in now, we know that for the reaction, the enthalpy is going to be 3257.5. And now the reason that it would work both ways is because you're going to be creating double, right? So if you're creating double and you leave the enthalpy as double, the ratios are going to be the same. So that's why you end up getting the same thing. Does that kind of make sense? Okay, so this is the enthalpy we're going to use for now. So the moles times the enthalpy of the products. So what do I put?
12 multiplied times. Would you divide also the value of that you're given, like negative 393.5 by 2, or you keep it that way?
You would keep those the same.
Okay.
The only thing that changes that is the moles that you're multiplying by.
Okay. So it will be 12 times that. 12 times negative 393.5.
Mm-hmm.
Well, in this case, 6, I guess, because we're using division divided by half.
So someone said in the chat, are you talking about the new enthalpy of formation? Let me double check our math.
Yeah, that's what I got too.
Divided by 2. Yeah, it should be that. So be careful. 3, 2. I might have just misheard you all. 6. And this is going to be a 6. Okay. So our products here, remember that we reversed. Yasmin, wouldn't it be 15? Where did you get the 15 from, Yasmin?
5 times 10 to the negative.
I think it might be because of the division.
15 divided by 2. Okay, but remember that if an element is in its elemental form, what is the enthalpy of its formation? 0, right? So let's look at this equation that we made. So we're going to have 15, let me put brackets, 15 over 2. Either way, it's going to be 0. And then this is our product. So we already have that over here because that is what we are, that's the formation that we're looking at. So now we're going to have minus the reactants, which are 3 times water. So the water is negative 285.8. And then this is the summation. So plus the coefficient of carbon dioxide. And the enthalpy for that is 393.5. So I ran out of room. Okay. So we have 327.5. Okay, so this goes to 0. We have a negative plus a negative times a negative. So we know we're going to get, what the heck? Yeah, I messed up here. So we're looking for, what did I do? Okay. So yes, we should have put plus here the formation of C6H6. There we go. So C6H6, and then this is going to be plus. So what do we get when we add that all up?
I got 3218.4.
I got that too.
3218, yes, 0.4. So we'll subtract that from both sides. And what do we get? 3267. Okay, so then we get the enthalpy for C6H6 equals 49.1. Is that what you all got?
Yes.
Yes.
Okay, cool. Okay, so did everyone see how I did that? So be careful which approach you take. You can do it both ways. You just need to keep track of if you switched the equation or not. So be careful because some of you were saying that we should plug in, I think we said oxygen as a product instead of a reactant or some way the other way. Just keep track of that and you'll be good to go. And keep track of your moles and things like that. But the essential concept from this question is this reaction. So know that the enthalpy of the reaction will be summation of the moles of the enthalpies of your products times or minus the summation of the moles times your enthalpy of the reactants, right? Okay, so let me clear this. I know we wanted to do some gas problems, so I will cover one more problem from here and then we will go ahead and go over to gas laws. Diego, can you scroll down, please? Oh wait, is it gonna let me? There we go, okay. Which of the following would be exothermic? Okay, so this has to do with change of states, right? So if we're going from solid to gas, is that exothermic or endothermic?
Endothermic.
So this is endothermic. And liquid to solid?
Exothermic.
Okay. So that might be a good option for now. Let's see if any of the other ones are. Liquid to gas?
Endo.
Endo. Solid to liquid? Endo. And solid to gas is endo. So yep, that was the correct answer. So it should be B.
How does liquid to solid give us exothermic?
Liquid to solid. Okay, so we are going from, you have to kind of think about the particles, right? So if we're going from liquid, they're very like, think of gases. They're moving around a lot, right? They're moving around a lot. Liquids, they're a little bit less. Solids are even less. They're super packed, right? So if you're going from disordered to even more ordered, you are going to release some energy, right? There's going to be less energy in something that's very compact than something that is, disorganized like a gas or a liquid. So you kind of have to think of it in extremes. Think of if you're going from, think of it in a spectrum, gas to liquid to solid, right? So very disordered to very ordered.
I have a good example if you guys are struggling, like remembering how a reaction is exothermic or endothermic. If you put water in a cooler or like a cold container, what does it release heat or does it gain heat?
It releases it?
Yeah, it releases heat. And so when you have water going into a freezer, it turns into ice. So that's from liquid to solid. So it releases that heat that the water has to create the solid.
Oh, okay. All right. Okay,
So,
that's good. Thank you.
Yeah, that's a good example. And then if you go backwards, you absorb heat. Like if you're holding a piece of ice cube in your hand, the ice cube absorbs the heat from your hand, therefore turning into water, and it melts. So that's a good way to sort of remember it.
Yeah, that's
really
another.
Good. Oh.
Yep.
I was gonna ask, what's another example of an exothermic that you guys can think of?
Another one, do you remember Philip used to talk about it, like when you perspire?
I never had Philip.
I'm trying to remember how he explained it. He explained it so well. So when you are sweating, perspiring, right, you're letting off heat. And what happens when you let off heat? Like, what is sweating? You're turning like from just yourself to liquid, right? Does that kind of make sense? Or like when you put, let's say, water like on asphalt and it's hot, it goes from liquid to gas. So the asphalt is absorbing the heat. Does that, I can't explain it. I can't explain it as well as Philip and how you did.
I can't think of any other ones. The only other example is I know there's some metals like gallium. If you hold them in your hand as a solid, the heat from your hand can actually melt the metal. So it goes from a solid to a liquid because it absorbs the heat.
So is exothermic absorbing the heat?
No, endothermic is absorbing the heat.
Oh.
Exothermic means that it releases the heat.
Okay, thank you.
Exo, kind of like exiting. That's another way I like to remember it by.
Got it. Thank you.
Okay. Do you want me to scroll it down or?
Yes.
Okay.
Um,
Well, you guys said a gas one. Do you guys want to continue doing these? These are all enthalpy.
is there a gas like I have some examples for gas laws.
This
but
one
it
is
doesn't-
a partial pressure one if you want to do that one.
Okay, we can. I don't remember who it was that asked the question about gas laws, but would you like? Oh, sorry. Go ahead. Would you like to do the partial pressure, or would you rather like the ideal gas equation ones?
Can we do this
Well,
partial
personally,
pressure?
oh, okay. Yeah, honestly, I think that the partial pressures I have less trouble with, but the like the ones where you have to identify the law, that's the ones I have a little more trouble with. So we can do like both if that's not a problem.
We do both, like 1 and 1.
Yeah, we can go ahead and do this one, and then we'll move on to the ideal gas.
So do this one, Paulina, and then I'll take over.
Okay. Okay. So a gas mixture has a pressure of, so this is our pressure, 30.44291 millimeters of mercury at 777 Kelvin. The mixture is analyzed and found to contain 12.271 moles of carbon dioxide. So let me put this at N. Okay, so 1.0401 moles of carbon monoxide and 0.875 moles of argon. What is the partial pressure of carbon monoxide in atmospheres? Okay, so actually let me erase this. Okay, so it's asking for the partial pressure of carbon monoxide. How do we find partial pressure? First, we need to find the mole fraction, right? And how do we find that?
You would add up all the moles that it gave you.
Mm-hmm. So
And
let's
then,
add
yeah.
exactly 12.271 plus 1.0401 plus 0.875. Okay, so we're going to add that all together, and what do we get from that?
I got 14.1861.
14.1861. Yeah, okay, and then so this is our total moles. So if we want to get the mole fraction of carbon monoxide, it will be our moles of carbon monoxide, which was 1.0401 over our total moles, so 14.1861. And what do we get?
Got 0.0733.
Yes. Okay, so 0.0733. Okay, so this is our mole fraction. So to get the partial pressure of this gas, we're just going to multiply our mole fraction times P total, right? So we get 0.0733 times our total pressure, but they give us pressure in millimeters of mercury. So can we leave it like that?
No.
We have to convert to atmospheres, right? So 30.44291. I don't know why they give you so many decimals. Okay, and then what is our conversion?
Divide by 760.
Yes, 1 atmosphere.
1 atmosphere is Celsius.
Yes. So 30.44291 divided by 760. And we should get 0.04 atmospheres. Is that what you all got?
Yes.
Okay, so we multiply that by 0.0733. We should get, let's leave it in scientific because that's how they have it, 2.937 times 10 to the negative 3 atmospheres. Then it should be 8. Is that what y'all got?
Yes.
Yes.
Any questions about partial pressure?
I have one question. Where do you get the 30.44? Is that a constant? That's the constant, right? Or
Oh, so they just told you that that was the pressure. So a gas mixture has a pressure.
oh, okay. Yeah.
Yeah,
Sorry.
so you're just given that. That's the total pressure that you'll use for this one.
Okay. Yeah. I use on the question. I got lost. Thank you.
No, don't worry. Okay, so they also gave you the temperature here. So does that matter?
No.
It doesn't matter, right? For our partial pressure equations, that we don't use that. Okay. So Diego, if you want to go ahead.
Sure. Can you clear your drawings? Or is there someone that's still? Oh, it's being recorded. I forgot.
Yeah.
Okay. Let me see. Let me find a good one for the gas laws. Who's the volume evolved? These are all enthalpy. Let's work.
I think that one's good.
Yeah. Okay. So first of all, I want to show you guys a quick trick on how to remember all the Charles, Boyle's, and Guy-Lussac's law. Not Gay-Lussac's, okay? It's Guy-Lussac's. That's how I remember it. But if you guys are still struggling remembering all the laws, you guys can actually derive it from using one. RT, R1, and then T. Oh, well, that one actually doesn't matter because R is always a constant. Okay. This you would equal it to 2 because we are looking at 2 systems. So if my pressure is constant, you would eliminate your pressure. Your moles are always typically going to be constant, and then your R is going to be constant. So you're left with V1 T1 equals to V2 T2. If you guys are doing per se, let's say if you guys have constant temperature, you guys can cancel out your temperature and you're left with P1 V1 equals to P2 V2. And then if you guys are looking at, let me erase the R. If you guys are looking at constant volume, you guys can cancel out your volumes because they're constant on both sides, and you're left with P1 over T1 equals to P2 over T2. Is there any confusion?
Yeah, what do you mean by looking at? Like, as in, like, what the problem mentions?
Yeah. So let me see. So a bulb contains argon gas at 1 degree Celsius and a pressure at that. After the light bulb is turned on, the temperature rises to 50 degrees Celsius. And the final pressure of the gas, what is the final pressure? So let me erase this again. And
So essentially, like what we're saying is that you don't need to memorize the laws. Dr. Saupe won't ask you like what law did you use, like the names of them. As long as you know the ideal gas equation and you can like manipulate it, then you'll be good.
The reason why we have why we are relating like P1 PV over nRT to 2 times is because we are looking at 2 different sides, to like before and then after, if that makes sense. And RT Okay. So here, what is assumed that is constant? What is constant here in this equation?
Would one of them be volume?
Yeah, our volume is constant. Let me do that in a different color, actually. So our volume ends up being constant. What else is constant?
Moles?
Mold.
Yeah, our moles. There's no mention of any moles, so we'll assume those are constant, and then our R's are constant. So what equation do we end up using?
E over T.
Yeah, P1 over T1 equals to P2 over T2.
So whatever isn't mentioned is a constant, right?
We'll assume it's a constant. Yeah, we'll assume. We're not saying it is. We're assuming here. There's a lot of assuming later on in Chem 2 as well, so be ready for that. So what are my givens, first of all?
They give you the first pressure.
Yeah, I gave you my first pressure, my initial pressure, which is 0.3540 atmospheres. And then what else?
T1.
My T1, which is 1.00 degrees Celsius. So what is that in Kelvin? I might as well already convert it.
274.
274.15 Kelvin. Yes. And then what else am I given?
Your final temperature.
My T2, and that is 50 degrees Celsius. And what is this in Kelvin?
324.15.
324.15. Thank you. And thank you, Natalie, in chat. Okay, so do I have all the necessary variables to solve it out?
Yes.
Yes, okay, I do. Because I have my pressure, I have my temperature, and I have my other temperature. So I need P2, that's my unknown. So I'll go ahead and manipulate this equation. What do I have to do in order to single out P2?
Multiply by the second temperature.
Yeah, so T2 P1 over T1. I recommend, before plugging in numbers, I recommend writing out the equation. That's a physics habit for me. I used to be mechanical. It's easier to manipulate the equation without having all the numbers in. That way you don't get lost. And so I'll go ahead and start plugging in. So 3, here. So
Diego, for these problems, is temperature always Kelvin?
yeah, I would recommend converting to Kelvin. I just recommend
then
converting to the standard units that we use.
What would the standards be for pressure, volume? It
Well,
would be like,
if we look at PV and RT, temperature would be Kelvin, our volume would be liters, and then our pressure would be atmospheres. And then moles.
Okay.
Yeah. Basically, whatever your R is, because R is R is liter atmospheres per mole Kelvin. So yeah. And then so T2, so that is 324.15 and times P1, which is 0.3540 atmospheres. And then if someone can please tell me what we get.
Excuse me, Diego. So I told you wrong. T2 is actually 323.15.
Okay, thank you. That's all right. No worries. And then if you guys can tell me my temperature, or sorry, my new pressure.
0.
I got 0.4.
Whoa.
Go
ahead.
I got
0.4173 is what I got.
4173. Is that what everyone else got?
Yes.
Okay. And is that what Dr. Saupe got? I don't know if that's what he got.
yes.
Okay.
Yes.
All right. I'll take yes words. Okay. So yeah. So it would be D in this case. Awesome. Any questions? Anyone confused about this?
No.
Nope. Pretty good.
Sounds good. All right. Let me see. We have a little less than, we have 12 minutes. Oh, no, not 12 minutes. Sorry. We have 22 minutes left. So we can do a couple more problems. Is there a specific problem you guys would like me to do, or?
I had a question for one of them.
Which one?
For number 2, it's like the second question, like the second problem with number 2.
So the second problem is.
No, the other one. Sorry.
Oh, the other two. Okay.
Yeah.
This one.
Yes.
Okay. So here we have 0.1 kilograms of aluminum metal that is at 100 degrees. It is placed in 500 grams of water, which is at 25, and we're asked to solve for the final temperature. Okay, so what equations am I going to be using first of all in this problem?
The Q equals ms, change in temperature.
Yeah, Q equals ms delta T. And then there's one other equation that we have to use.
Q equals negative Q.
QA equals negative QB. Okay, and then what are my givens?
Another question on when you're finding.
Do I have, so what are my givens? So we have aluminum, and then we have our water, because those are my two substances.
100 kilograms of aluminum.
So the mass of aluminum, we have 0.1 kilograms, and then what is this in grams?
100 grams.
Yeah, 100 grams. There is a piece of information missing that Dr. Saupe did not provide.
Yeah, that's what my question was, for the specific heat of aluminum.
Yeah, I would say you guys would have to look it up in that case. He should give you guys the specific heat for that one, because if not, I don't see how you guys would be able to. Use 0.9 for the specific heat. So that's the piece of information he forgot. 0.9 joules per gram degrees Celsius. Okay, and then is that, what else am I given for my metal?
The initial temperature.
Yeah, my initial temperature, my T naught, which is 100 degrees Celsius. And then my mass of water, my specific heat, and my initial temperature of water. What are these numbers?
500 grams.
500 grams, my specific heat.
4.18.
And then my temperature, 25 degrees. Okay, next, who's gaining and who's losing heat?
Water
Isn't
is
the
gaining
metal
heat.
losing heat and
Yes.
the water gaining?
Yes, the metal is losing heat and the water is gaining heat. We know this because our temperature for our metal is really high, and then our temperature for water is really low. So whenever you place them together, let's say in a cup, the metal will come down in temperature while the water will go up in temperature until it reaches that equilibrium. Okay, and then, all right. So what's next? What do I need to do?
Convert your kilograms to grams. Oh wait, no, never mind. Sorry.
We already did that.
Well, isn't it like just plug in like everything to the formula?
Yeah, so now I can plug in everything into my formula. So this is the aluminum. Oh shoot, wait, I wrote that wrong. So, are you guys sure we have to convert for Kelvin here?
We're not gonna do that.
No, because we're working with the change in temperature.
And not because we're working with change of temperature, but the reason why is because we have a delta. We're working. Our specific heat is in degrees Celsius, so we don't need to change our temperature.
Real quick, how did you go from 0.100 kilograms to 100 grams?
So 0.100 kilograms, and then so how many grams are in a kilogram? I like to have the bigger unit and have the one.
Is it 1,000?
Mm-hmm. Yeah, 1,000 grams. So when you multiply 0.1 times 1,000.
Oh, okay, got it. Thank you.
No worries. Okay, so sorry if I'm acting a little distracted. There's like something going on in the background too. Okay. So let's go ahead and assign this. So QA of H2O equals to negative Q of aluminum. And then, so yeah, you guys said I have all the units, so I can plug it in. So the mass of H2O, the specific heat of H2O, and our change in temperature equals to negative Q of aluminum, the S of aluminum, and the delta T. So go ahead and plug in your units or your numbers. 500 grams, 4.184 joules per gram degree Celsius. T final minus 25 degrees equals to negative 100 grams, 0.95. Oh no, it's 0.9. Sorry, that's my J. My J's are messy. J grams degree Celsius, and then ETF minus 100. Okay, so
sorry, one question. The 0.9 to search it up, right? That's
yeah, you'd have to search it up. In this case,
okay.
you guys weren't given to it.
Yeah, I just wanted to clarify where you got it from.
Okay. Yeah, I looked it up. Plus, yeah, it didn't look like Dr. Saupe gave it to you guys. So yeah, 0.9 joules per gram degree Celsius. Okay. So what do I do?
Distribute.
I distribute. So I multiply these. Okay.
And then you get 2092 for that.
So 5,000 times it's 2,092.
Yes.
Okay. And then over here.
90.
And then 90. Okay. Okay. And then, okay. So now what's my next step?
Distribute.
I'll distribute again. So here I have 292 TF minus, don't know what that number is. And then I have negative 90 TF plus, and I don't know what that number is.
The first one would be negative 5,200. No, 52,300.
There you go. Thank you. And then over here.
Positive 9,000.
Okay. And then pretty sure the rest is pretty straightforward, right? Next part, we do algebra. So I add the 90, and then I add the 52,300. So what's my new value for TF?
I got 28.09 degrees Celsius.
Oh, I haven't solved it out yet. Sorry. 282 TF, and then what is the value once you add the 52,000 to the 9,000?
So 61,300.
Yes, 61,300. So divide 0182, 0182. So TF equals to, sorry. Yeah, I got 28.09. Is that what you guys got?
Yes.
Yes.
All right, so B would be our answer. Any questions?
I have a question.
Sure.
So just to make sure, the element that has the highest temperature, that's the one that would be negative Q?
Mm-hmm. Yeah.
Okay.
That's the straightforward. All right, we have time for one more problem, I think. If anyone wants to recommend one, if not, I'm just gonna pick one randomly.
Diego, I just have a question before you continue.
Sure.
What would be like a scenario where we use the equation that's just like plain PV equals nRT?
Wait, I'm sorry, what was your question?
Like what information would be given by a problem where we have to use the equation PV equals nRT? Like logically. Or do we not use that?
It would depend what you're working with. I'm not really sure you would use gases with calorimetry. Paulina, have you seen that where we have to use the ideal gas law?
No, I haven't seen that with calorimetry.
I see it more with work because work actually deals with pressure and volume changes. I wouldn't say it deals a lot with calorimetry because calorimetry deals with heat.
Oh, okay.
Mm-hmm.
Okay, thank you.
No problem.
I have a question for number 2, like the one on the first page. We got a different answer right now that Paulina did it, because I think the answer key has the answer as A and not B.
Don't remember.
Oh yeah, I think there was an error in the converting the kilojoules to joules. So yeah, Dr. Saupe's answer ended up being smaller than the one you.
Oh, so the answer is B?
The answer is A on the answer key.
But it should be B.
I think it's because we also did it at workshop, and I looked at the paper and it was also A, but I don't remember how to do
I think it's because we have to divide the givens and the equations by 2 also, since we divided it like by the final equation, and that's why he got, it's basically the ratio, it's basically the answer you got divided by 2 because of that.
So what happened earlier is I noticed, because I also saw that. I just saw that Paulina's when we were doing the problem with her, she added an extra 0 by mistake to the 1720 when she converted to joules. That's what happened.
Oh, okay.
Yeah, but it was like, yeah.
Okay.
Oh, I did. Yeah, I remember now. Okay.
But it looks to me like he gave us the change of H of solution is 17.20 kilojoules per mole. So wouldn't we have to convert that to just kilojoules and take the mole out?
Yeah,
per mole out.
Yeah, that's what. Yeah, that's here what Dr. Saupe did.
Okay, yes, I did.
Mm-hmm. And then he converted to kilojoules. Are you guys able to see it, or?
Yeah, I'm looking at like the answer key side by side, and yeah.
Okay. Okay, let me see. What's another problem is there any other problems that you guys would like us to do?
Can we do a work problem?
A work problem? Sure, let me find one. What is involved? HTTP. That's enthalpy. Okay, there we go. So here we have zinc reacts with hydrogen chloride to yield hydrogen gas in the following balance equation. If 0.85592 grams of HCl reacts with excess zinc, how much work is done in joules? If the whole reaction is, okay. So this one's similar to actually question 2. This one's actually really similar to question 2 that we did earlier. Let me go ahead. Where is it? Okay. I missed it. There it is. Okay. So initially, what is our volume for? So in these types of cases where you have a reaction, I would say use the products in order to derive how much work there is. So initially, what is the volume of H2 before the reaction happens?
Zero.
Yeah, it's 0. 0 liters. Before the reaction happens, we don't have any hydrogen gas. So we didn't have a volume of hydrogen gas. And then after the reaction happens, so our final volume, will it be bigger than or less than 0? I worded that very weirdly. Go ahead, sorry.
Oh, is it bigger?
Yeah, it would be bigger than 0 because our reaction would happen and then we would actually have now hydrogen gas present in our container wherever we're solving for it. So how do we know how much hydrogen gas we have? What do I have to do?
Would you have to turn the grams that it gives you for HCl into moles and then convert it over to the other side?
Yes, you would. So we have 0.85592 grams of HCl. We also have our pressure of 1.211 atmospheres, and then we also have a temperature of 27 degrees Celsius. Okay, so yeah, we have to convert this to moles. So how do we convert this to moles? I know I kind of set it up, but what do I have to divide it by?
The molar mass.
What is my molar mass? Sorry.
Mm. 36.458 grams.
And then how many moles would I have then?
Uh, 0.023.
0.023 moles of HCl. And then, first of all, is my equation balanced?
No.
Yes.
Yeah, it is balanced.
Yes, it is balanced.
So what would be my ratio to convert to, we're working with hydrogen gas. So what would be my ratio?
So it's 1 mole of hydrogen gas for every 2 moles of hydrochloric acid?
Yes. Oh, I don't know why I'm writing HCl, H2O, HCl. Okay. So how many moles do we have then?
0.012.
Sorry. 0.01. 0.012 moles of H2. Okay, so how do I find out how much volume I have now of H2?
Can we use
Don't you have to plug it into the PV equals nRT?
Yes, we do use our ideal gas equation here. PV equals nRT. Do I have all the variables to solve for volume?
I have a question.
Sure, go ahead.
So how come we are converting it to H2? Because in the question, it says that it reacts with excess zinc. So wouldn't we?
So the reason why, so here it doesn't specify what we have to use in order to, it's sort of like a limiting reagent problem where we're trying to find out like how much product we can make of each one. Here I just chose H2 because I don't know, it seems simple to me.
Okay.
But yeah, that's the main reason. But the other reason why is because initially we don't have a volume for H2. That's the initial conditions. So before the reaction happens, we didn't have a volume of H2. After the reaction happens, we do have a volume. So whenever our delta V happens, we would have our final volume minus 0, making our delta V very easy.
Okay, thank you.
So we divide by P. Do I have all the necessary variables to solve for volume?
Yes.
What do I have to do to my temperature though?
Convert to Kelvin.
And then what number is that in Kelvin?
300.
300.
Yeah, 300.15 Kelvin. Okay. And then,
Diego,
yeah, what's up?
this is like a dumb question, but how did you decide to use that formula?
PV and NRT?
Yes.
Well, well, it doesn't state it, but we're assuming it's an ideal gas. It also, hydrogen is a gas. So that's also another reason why I'm using PV NRT.
Wait, one question.
Sure.
Before you started like working it out, you said it was a work question. That's where I got confused. Because you know that there's like formula for work, right? Besides that one.
So work is equal to negative P delta V.
But you didn't use it, or did you?
I haven't used it yet.
Oh, okay. So
because the reason why is because I'm trying to find out what my final volume for hydrogen gas is.
Oh, okay. Sorry.
Because initially our volume is 0, and then once it reacts, we do have a set volume. So that's why I'm trying to find out my volume change.
Yeah. Right.
Diego, but with like, I'm sorry, but like this formula,
which formula?
The PV equals NRT, right? How come last time we were like deciding what not to use with the PV over NRT?
The reason why is because here we don't have a pressure change. Here we don't have a temperature change. Here we just have a volume change.
Oh, true. Okay.
So we don't need the initial conditions of the volume because PV equals NRT. If we were to do our initial conditions, our moles would be 0 because we have 0 moles of H2.
Oh, that's true.
So that would effectively make everything else 0.
Oh, okay. I was so confused. Thank you.
Yeah, no problem. Yeah. Okay, so did anyone derive the volume, by the way? 0.012 moles, 0.0821, 300.15, and then we have our pressure of 1.211 atmospheres. Okay. Did anyone derive the volume?
I got 0.244.
0.244. Let me just double check with you guys. Can someone second that, please?
I got the same thing.
Okay. 0.0821. Okay, so this is liters, right? If we were choosing yeah, you would technically, you should have the same answer. I'm not guaranteeing it. If you want to, you could also, well, actually, hold up. Yeah, the ratio here for, if I were to use zinc chloride as an example, the ratio is still the same. So you would still have the same number of moles. So you would still have the same volume technically. Okay, and then, I'm sorry?
Why do we have to do the ratio? I'm really confused on that.
So the reason why we have to do the ratio is because we're converting from HCl to H2. Because we chose H2 as our subject to find out how much volume we changed.
So because it's like the one in the question, HCl.
Yeah. Well, HCl was given to us. We don't have a set mass for zinc.
So if it was like a different question with like, let's say zinc was the one with the 2 moles, would it be like the same thing, just different?
Yeah.
Okay, got it. Thank you.
And then so now looking at my work equation, which I have work equals to negative P delta V. Do I have my change in volume and my pressure to find out?
Yes.
Yeah, I have everything. So my pressure 1.211 atmospheres, and then my change in volume 0.244 minus 0. So what do you guys get as your change?
Negative 0.295 liters times atmosphere.
And then what do I have to do?
Multiply by the 101.
Yeah, I have to multiply by 101. So 101.325 joules, 1 liter atmospheres. So how many joules do you guys get?
Negative 29.9.
Negative 29.9, or if you're rounding, negative 30. So here, which one would it be?
Would it be E?
Yeah, it would be E. I would say E. Our initial volume is not 0. Is that, did he do this one differently? Oof. Oh, where is it? Oh. I hate these problems. Why is he using the volume of HCl? That doesn't make sense. Huh. I don't know why he's using the volume of HCl for that one. Paulina, did I do this problem wrong?
Let me look at the key.
Because he uses the volume of HCl.
Let me look at what you did. Zinc reacts with chloride. Oh, I think the entire reaction is maintained. I think because he gives you the because he's giving you the grams, but then you convert it, so that's fine. Give me 1 sec to look at it.
Oh, I see now. It's because it's gases. That the gases matter. Because initially HCl is gas, and then afterwards H2 is gas. Yeah, nice. Yeah.
So what happened?
So the reason why it's different is because so we do have to derive the volume change for H2, but the reason HCl is a gas, so that one does actually affect it. I thought it was because it was like substances, but it's not. It's just different substances. So 0.023 moles of HCl. Oh dear, I'm just messing up my writing everywhere. Okay, so the where I messed up here was we do have an initial volume. So if you guys remember, which one was the problem that you guys did? If you guys, okay, this problem. If you guys remember this problem, here we use CO2 as our subject. The reason why is because CO2 is a gas. Initially, we don't have any gases, so our volume is 0 because works with the gases, and PV and RT, this is the ideal gas, so this deals with gases only. So initially, our initial conditions, we don't have any gases, but our final conditions, we do have a gas. So that is why it's above 0. So the reason why in this problem, where the heck is it? So the reason why in this problem we have to use HCl is because HCl is a gas initially. You could say this is some of the work of HCl plus the work of H2O. I wouldn't say the work of HCl and H2O. I would see it mostly as the volume change of HCl and H2O.
So then what was the initial volume?
So yeah, so our initial volume, so we have 0.023. We have 0.0821, 300.15, and then we have 1.211 atmospheres. So our initial volume ends up being we get a initial volume of 0.468 liters. Is that what you guys got for your initial volume change?
Should be 0.47. Yeah.
Oh, yeah,
Where did you
0.4.
get the 0.023 from?
That's the moles of HCl.
Okay.
So then the second volume, we get it from the, when you divide it by 2?
Yeah, the second volume, you get it from HCl. And then, so here we're working with gases. So the volume of HCl does matter, and the volume of H2O affects it too.
I have a question.
Yes.
How do you know when you're gonna use all the information given? Because you know, like on this one, the grams of HCl, you use that to find the N and nRT, and then you use the ATM and the degrees Celsius. But I know there's other problems where they'll throw extra information to throw you off, but you don't necessarily.
It comes with, I would say mostly comes with practice. It doesn't really, there's no like, oh, if you only have this, you only need to use this and that. It comes with practice and understanding what we have to do for the problem. There's no easy way to like say like, oh, you're going to be needing that and that. Like, I don't know, which is an example of where we didn't end up using
I
anything.
didn't use the temperature for the mole fraction when I did.
Yeah, so let's find it. For this one, we were given our temperature, but we know that the mole fraction equation is the N of the gas over the N total, and then our partial pressure equation is X of the gas times our total pressure. So in this case, temperature doesn't affect it, so that's how we know temperature isn't needed in this problem. So it comes with this understanding how to do the problems.
Okay, and then a question kind of complex like the one that we just did. Would it kind of be like common sense in a way that you would have to, in order to get the answer that you want, you have to do many?
So a problem like the one we just did, this one's a complicated one because you have to understand that work works with pressure and gases and volumes. So you have to use your ideal gas equation, you have to use the work equation. So that's how you know what you need for each problem.
I think.
And using the, oh, sorry, what?
Sorry, go ahead. I'll say it right now.
Oh, when you mentioned like using the mole fractions, that's when you're trying to find something out of a different compound? Or when would you use mole?
Well, it depends on the problem. Like here, we're asked for a partial pressure of carbon monoxide. So we have to use the mole fraction since partial pressure uses the mole fraction. Okay, it is 6:42. You guys are actually technically free to leave. Oh, we got 30 people, so some people did leave. But you guys are free to leave. I'm gonna go ahead and stop the recording actually.